Okay, great. Thank you everyone for joining us for our third session in this quantum control and state preparation block. I'm very excited to say today we're going to have three really exciting talks from essentially PhDs and postdocs within the area, working within the area of quantum control and preparation. But before we start on that, there's a few announcements. Most of you will probably get tired of this. If not, please listen and act on it. We have a very exciting virtual poster session being held on the 16th and 23rd of June. This is really to enable all of us to sort of come together and present, and great opportunity for PhDs and postdocs to also discuss with each other and network. We'll be using something called GatherTown to enable and facilitate that networking, and it's a really exciting platform. To engage with the process, there's two ways. Of course, you can submit your posters. If you're unsure on the links and stuff, contact either of us, any of us within the committee. Sophia, correct me if I'm wrong. I'm probably putting issues here, but I think there's a price, maybe.
That's right. So we're actually giving out a poster prize for each session. Sign up. It'll be great. It's £100 price.
Wow. All right. That's really good. I didn't realize it was that good. Okay, so all the motive to sign up. So I look forward to looking at all these posters then as well. So there's that, and of course there'll be the entire block as well, community block, which we'll advertise soon. The next thing we have immediately not next week, but the week after, we have a break next week, is the final part of this block 4 on quantum control and state preparation. And I'm really, really excited to share with you a panel discussion that we'll have called Beyond the Quantum Ground State, and of course focus within the regime of optomechanics. It will be chaired by Michael Vanner from Imperial College, and we'll be joined by Tracy Northup, Ewald Verhagen, Andre Zirup, and Yivin Chu. I think there's actually an error in the photo for some reason in this photo. That's not the photo of Yvonne, but we'll correct that when it goes out. Apologies for that. So that's on the 9th of June, 2021. Yeah, that's this year, and it's at 2 o'clock. So really excited discussion to happen there, and really would be great to have everyone on board. So without further ado, let me introduce our chair for today. That will be Sabah Khan. She's a PhD student, first-year PhD student at University of Lancaster, working with Edward Laird. And Sabah, so thank you for chairing for today. And she's also, let me quickly add, doing a lot of the work behind the scenes at the Unicorn Committee. And so a lot of the great stuff and publicity that you see is from her. So it gives me a great honor to introduce Sabah. And Sabah, the floor is yours.
Thanks very much, Mudassar. It's a great pleasure today to have 3 early career researchers, Dr. Ricardo Puebla, Clara Ventura, and John Price. And the first talk will be given by Dr. Ricardo, who is originally from Madrid, Spain, where he did his undergraduate studies in theoretical physics and MSc in nuclear physics, both at Complutense University of Madrid. And in 2013, he started his theoretical physics group led by Professor Martin at Ulm University in Germany. And the main focus of his thesis was on quantum critical phenomena in light matter interacting systems and the universal feature emerging in the non-equilibrium dynamics. And 2018, he started his first postdoc in quantum technology group led by Professor Mauro in Belfast, working in different aspects of open quantum systems and quantum thermodynamics and quantum control. And since January 2021, he is a postdoc researcher at IFFCSIC in the group led by Professor Juan Jose in working on quantum optics and information processing. And today he will be talking about quantum control in spin-boson systems via shortcuts to adiabaticity. So, Ricardo, the floor is yours.
Thank you very much, Saba. I hope you can hear me all right.
Yeah, I can hear you.
Thank you very much for the introduction, and also thank you for the organizers for setting up the stage and giving me the opportunity to talk about my recent research on quantum control using shortcuts to adiabaticity. So the outline of the talk is going to be the following. So basically, I will introduce the spin-boson system that I'm going to use for quantum state preparation. Basically, the Jaynes-Cummings model, which is a fundamental model in many different areas of quantum platforms nowadays, right? Then I will introduce how to use shortcuts to the adiabaticity in order to prepare interesting quantum states. And as an example, I will give you the details of how to produce or how to generate Schrödinger cat-like states of superposition of Fock states, and also photon-shifted states that are very similar to photon-added states, but featuring more non-classicality. And finally, I will give a brief summary of the findings. And just to say that everything I'm going to talk about today it was published last year in this paper here in collaboration with Obina Abba, a postdoc in the group of Mauro Paternostro, who was the last author of the paper. So let me start with a brief discussion of the Jaynes-Cummings model. So basically, as you all know, probably the Jaynes-Cummings model describes an interaction, a coherent interaction between a single spin or a two-level system described by the usual Pauli matrices, right? Interacting with a single mode, a single bosonic mode. And basically, in this model, they interact through this interaction term, which conserves the number of excitations, the total number of excitations, right? So you have these two processes happening. You can excite the atom at the expense of absorbing one boson and the other way around. And as you all know, probably this model is relevant in many different quantum platforms. So basically going from cavity and circuit QED, where you can have an atom or an artificial atom, like a superconducting qubit, interacting with a single bosonic mode, which is the electromagnetic field, right? But also applies to other setups, like in trap ions, where you can couple the internal degrees of freedom of an ion with the motion in the trap, and also to other setups like optomechanical systems or nanomechanical resonators coupled to a two-level system, which can be like a defect in the membrane, like in this scheme here. So there are plenty of realizations of this model, and all of them, they feature different properties and different parameter regime, right? But interesting is that in these regimes, in these platforms, basically you can tune the frequency of your spin, and typically, and also the interaction strength sometimes, right? Like for instance, in this optomechanical system, where you can have you can modulate the interaction by tuning a magnetic field or the gradient of a magnetic field in this case. So the Jaynes-Cummings model basically allows you to complete a population transfer between different states, right? Like for instance, this is a typical Jaynes-Cummings ladder, where you have the ground state of the spin and going up the number of excitations of the bosonic mode. So basically the focus states. And this model basically couples this pair of these pairs of states, right, in this diagonal here, and conserving the number of excitations. So it means that if you have one state, like for example the G1, you can complete the population transfer if you are in the anti-resonant condition, right? So basically the frequency of your spin is equal to the frequency of your mode, and then you can complete this transfer in this time, right, where you have this interaction constant or this coupling constant lambda. This means that basically you see here this n, this is square root of n. This means that it is not possible to perform this population transfer in all the subspaces, so basically in all these states at the same time. So you will have a mismatch given by this dependence on the on this square root of n, right? That gives account of the number of excitations within each of these subspaces. So one way to overcome this problem that will be useful for quantum control and state preparation is to use basically an adiabatic evolution. So basically a time-dependent control of the parameters of your Jaynes-Cummings model. Now let me just say that basically given the simplicity of this model, you can diagonalize the Hamiltonian in each of these subspaces, right, where the number of excitations is conserved, as for example, basically given here by these two eigenstates, where phi is the mixing angle depending on the tuning of your system, basically how different is your frequency of your spin respect to the frequency of your mode, and also the interaction strength in lambda. And as well, of course, as the dependence on the number of excitations within your subspace. So basically, what you can see here is that in general, you will find these eigenstates of the Jaynes-Cummings will be a superposition between the En and the Gn+1, basically a superposition between these two states. And one way to complete the population transfer is basically tune this mixing angle from one string condition to the other, where basically you will go sweeping this mixing angle, right? If you do it very slowly, basically by tuning the tuning or the interaction strength in time, you can go, basically you can complete this population transfer from this state to the other or the other way around. And this is basically the common picture in the Landau-Wiener problem. So in a way, the Jaynes-Cummings model basically turns out to be just a collection of n Landau-Wiener problems. Well, in theory, infinite Landau-Wiener problems, because the bosonic mode is not bounded. So, and just to remark that if you do this, basically tuning this angle in time, you will achieve this population transfer in all the subspaces if you do it slowly enough, right? So if you do it in an adiabatic condition. So of course, the price to pay in that case is that you will need to do this time dependence or time dependent control of your Hamiltonian very slowly, and therefore it is not of practical use, because then the coherence will kick in and it will spoil the quantum state preparation. So one way to overcome this problem of the required infinitely long time in order to prepare the state, basically what we can do is to resort to shortcuts to adiabaticity, which is nothing but a way to control the system in a way that basically you don't create a non-adiabatic excitations. So this was proposed in different papers, and it has been applied in different areas such as quantum thermodynamics and non-equilibrium quantum critical phenomena and so on. And basically the crux of it is that you can have your Hamiltonian, your time-dependent Hamiltonian, that you can write it in an instantaneous eigenbasis like this, and then you will add another piece to your Hamiltonian that takes this form. So basically it will counteract the number of excitations that you are naturally putting in your system by having a time-dependent process. So if you include this extra control in your system, then you will have this STA, this shortcuts to the adiabaticity Hamiltonian, that will perform essentially an adiabatic evolution in a finite time, in any finite time. So one sketch to see this is basically here. So you will start with your initial state, and then you will perform your time-dependent control. And in general, you will arrive to a non-adiabatic result. So basically, it will follow a non-adiabatic evolution. However, if you perform the process very slowly, so meaning that you will take infinitely long time to perform it, then you will find this adiabatic evolution. So you will go to this red dot here. And what the shortcuts to adiabaticity is telling us is that it is possible, by at the expense of introducing another control in the Hamiltonian, by it is possible to achieve this adiabatic evolution in a finite time. Of course, the price to pay here is that you need to include a further control in your system. In the case of the Jaynes-Cummings model, just coming back to it, basically you can work out the conditions and you will find this extra control that you need to implement in the system, where this theta depends on t now, and also depends on how you choose in the first place your control of your original Jaynes-Cummings model. Of course, it has an ugly form, but the important thing is that you can, in principle, by choosing the original control in the Hamiltonian, you have a recipe in order to compensate this non-adiabatic evolution and find always exactly the adiabatic one. From a practical point of view, this is perhaps not very convenient because it requires to include a further control in your system. So there is another possibility is that you can transform this Hamiltonian here by using the so-called local content-adiabatic driving. So basically, you can apply a unitary transformation to this Hamiltonian, and you can bring it back to the original form of the Jaynes-Cummings. But now the frequency of your spin and the coupling constant will have a modified form. This is in this way, basically, you can mimic again the adiabatic evolution, but at the expense of having a different control of these two parameters that we assume that are controllable in your system. And one thing that I would like to stress here is that the new control in this Hamiltonian has a dependence on the number of excitations, as you can see here. So basically, you will have the original control that you want to apply, and then you will have a correction. But this correction depends on the number of excitations as well. So this means already that you cannot perform exactly an adiabatic evolution in different subspaces in the Jaynes-Cummings. So it will be possible if you address only one, and it will be an approximate result as soon as you want to perform the population transfer in all the Jaynes-Cummings ladder. More precisely, in the way in which you can construct these protocols is basically assuming that the control Hamiltonian is equal at the boundaries of your control. So basically starting at time 0 and at the end of the protocol, both Hamiltonians match with your original Jaynes-Cummings. And also you need to ensure that the functions of the protocols are smooth at the beginning and at the end. So basically, one possible protocol that you will need to follow here will be to tune the frequency of your spin using this black line here, right? This will be the original proposal for the control, as well as the coupling strength. And what the local content-adiabatic driving is telling you is that depending on the number of excitations of the subspace that you want to address, you will have a modified profile that basically has an analytical form, but it has been plotted here for different subspaces. And you can see that there is small differences depending on the number of excitations, as well as for the coupling strength. So these protocols depend on the specific subspace n, and in principle they allow to perform exactly the transfer in any finite time tau between these two states. As soon as you want to do in a collection of them, this will be an approximate result. And in addition, I would like to stress as well that depending on the experimental constraints that you have in your system, so for instance, the maximum value that you can achieve either for the frequency of the spin or the frequency of the interaction strength, sorry, and this can be included in your protocol as well. So here just an illustration. Okay, so with this, I would like to use these protocols in order to construct these Schrödinger cat-like states, as well as a photon-shifted. So I will start with the cat-like states of basically a superposition of Fock states. And in order to do that, basically, let me assume that you can start with a Fock state here in this Jaynes-Cummings ladder. So basically, this will require to cool down the bosonic mode to the ground state, and then perform this first Fock state preparation that you can do as well with the STA, but there are also easier ways to do it. But anyway, let me assume that you have this state here. So what we can do is basically now apply a pi pulse, a pi half pulse to the spin. So you basically split the population in half in this Jaynes-Cummings ladder, and then you can apply the STA control. So basically, by doing the STA control, you basically transform all the population from these states in these different subspaces. And then you can apply again a pi half to the spin. And finally, you can postulate or basically apply a projective measurement into the spin. And with that, for instance, in this case, if you postulate the ground state of your spin, then you will be left with a coherent superposition of the Fock states 0 and 2. And this is just an illustration, just an example for this particular case. So basically, here you see the beginner function of this Schrödinger cut state, and the fidelity to obtain this state is very, very high. And it depends on as well on the specifics of your setup. But in principle, this fidelity can reach very high values. And just compare it, if you don't perform the STA, if you don't perform the control that I was mentioning before, basically you follow the bare, or basically without control, then you will obtain a very poor fidelity. This is just one example. So of course you can prepare cut states of farther apart Fock states, and as for example the 0 + 6 or so on and so forth. Of course, this result here is not exact. The fidelity is not 1, and it is due to the fact that that we are addressing different subspaces in the Jaynes-Cummings ladder. So basically, as soon as you address different subspaces,
Pardon, 2 more minutes, please.
Oh, okay.
Okay.
Yeah, thank you. Okay, so basically, just to say that this is possible to prepare this sort of states. Another interesting class of states is the photon-shifted, and that are akin to the photon-addition states. So basically, this state has been extensively studied in the literature. And what we can do here is do something similar, but not quite, because what we can do is basically to shift the populations in this Jaynes-Cummings ladder, but without including the amplitude that this A dagger creation operator will introduce into the state. And this will be achieved, this operation will be achieved by the STA to a very good approximation. So basically we will do that. And then basically we will remove the vacuum contribution into your state. And this doesn't require any post-selection. So basically, in order to illustrate that, we consider a coherent state. And by doing this STA control, the shortcut adiabaticity control, we dig a hole basically in the beginner function, basically because we are removing the vacuum from it. And as you can see also the entries of the density matrix basically are shifted by 1. And this is just a way to create non-classicality. And if you compare the non-classicality that you create compared to so by doing this photon shifting compared to the photon addition, what we find is that it's always the non-classicality by doing photon shifted, basically following this protocol, is always larger than photon addition. And this will be similar also for thermal states. And with that, let me just summarize the main findings of the talk. So basically, it is possible to perform quantum state engineering in a spin-boson system using shortcuts to adiabaticity. In this way, you can prepare states in a fast and robust manner. And as I show, basically, you can create these non-classical states like cut-like states and photon-shifted states. And while in the publication, where you can find more details, we focus on a Trappalion implementation. These protocols are amenable for the implementation in other state-of-the-art platforms. Thank you very much for your attention.
Thank you very much, Ricardo, for such a nice talk. So any quick question from him? Okay, if not, then you can reach out to him at the end of this session. So let's move to the second talk from Clara. So Clara, she obtained her bachelor's and master's degree in physics from Ulm University before moving to the University of Cambridge for her PhD in Professor Andrea's group. So without further ado, please go ahead.
Thank you for the introduction, Shaba. And indeed, let me start by thanking all of the organizers for putting together this nice seminar series. It's really a great pleasure for me to present our work here today that I did together with Matteo Brunelli and my PhD supervisor, Andreas Nonnenkamp. What I'd like to talk to you about today is a correspondence that we recently established between two concepts that have so far been studied separately. So one is directional amplification. I'll talk about this in a bit. And the other is a notion of non-trivial topology that is underlying the models that display directional amplification. So what is directional amplification? I think it might be familiar to quite a few of you in the audience because it's actually been realized with optomechanical systems before. What it means that when we probe a system, that the probe signal is transmitted and amplified across the system in one direction, but in the reverse direction, it is suppressed or completely blocked. And as you can imagine, this is really useful for numerous applications. So if we think about state-of-the-art quantum information processing, then you can imagine that it's really useful to read out superconducting qubits because it doesn't only allow us to amplify very weak signals, but also to protect them against noise and backscattering. So we have this phenomenon on the one hand, directional amplification. On the other hand, we have a notion of non-trivial topology. Topology characterizes shapes in mathematics, so or rather distinguishes them. In this particular example, what will be important for us is to distinguish different functions or curves in the complex plane. And in particular, we will distinguish them by looking at how many times they wind around a specific point, in this case, the origin. So here we would have a function that has a winding number of 0 because it doesn't enclose the origin, whereas here, these two have a winding number of +1. So these two have a distinct topology. And what we've shown is that we can identify such a notion of topology in systems that show directional amplification and that there is a one-to-one correspondence between the two. But let's take a look at this one step at a time, and let's start from an example system that displays directional amplification. Or indeed, let's take one step back and look at an isolator. An isolator is a device that shows directional transmission. Here's a minimal model for such a system that you could even implement with optomechanics if you like. And that consists of 3 modes. These are bosonic modes, could be cavity modes, for instance, and we'll focus on mode 1 and 2. So these are coupled in different ways. So once there's this, on the one hand side, there is this hopping Hamiltonian here that allows excitations to hop directly from mode 1 to mode 2. And on the other hand, there is this coupling, indirect coupling via this auxiliary mode C, which is quite lossy. And if it's lossy enough so that it decays faster than all the other relevant timescales in the system, we can actually eliminate this adiabatically from the equations of motion so that effectively this coupling looks like a dissipative coupling. And if you think about modeling this in terms of master equations, then we get this non-local dissipator that governs the evolution and this effective dissipative coupling rate. But the crucial thing to observe here actually is this phase theta. This is a phase difference between the two paths excitations can take from one cavity to the other, and is here included in the dissipator. But it could also be included here in the hopping. That doesn't really play a big role. And the crucial thing is that now if an excitation takes this path or the other one, it can pick up a different phase, and this can result in constructive or destructive interference, and this leads to non-reciprocity. We can see this quite clearly if we look at the equations of motions that describe the system. Here I wrote them down for the expectation values of the cavity fields. Now, at first, we notice that there is some decay. We the cavities have some decay rate gamma, which naturally comes in when we couple them, for example, to a waveguide to probe the system. Then there's also some local decay, which comes from the dissipative coupling. But then the crucial thing that we're interested in is the coupling to the other mode. And that is asymmetric, as you can see. So the coupling to the other mode doesn't enter at all in the first equation, but it does enter in the second. So this already shows us that there is some non-reciprocity in the system. And this becomes even clearer when we look at the scattering matrix, which relates an input, so when we probe the cavities, to an output at a specific cavity. And you can see with a specific choice of parameters for this system, we get a highly asymmetric scattering matrix. And indeed, in this case, we get perfect transmission from cavity 1 to cavity 2, but not vice versa. So now let's add another ingredient, which we like to call incoherent pump. Essentially, it just means that we incoherently add excitations to the system. You can think about this like, for instance, coupling to another mode that is out of equilibrium and decays quickly, so that when we eliminate this, it essentially looks like we are adding excitations to the system, or essentially just add gain. And in the equations of motions, this features like damping at a negative rate and enables gain. And we can see this in the scattering matrix as well. As you can see, I just replaced the transmission of 1 we had before with the square root of the amplification gain. So now we've got a minimal model for a directional amplifier. And in the next step, what we'll do is we take multiple copies of this system and just combine them together, so we get a chain of length n. So this system is now translational invariant, so this makes it quite easy for us to write down equations of motion in principle. But actually, we're not interested so much now in the details of the model, but we'll just focus on the general form of these equations. And these can be written as matrix vector product, as you can see down here. And this matrix is the crucial thing we need to focus on, because it not only governs the dynamics, it also crucially determines the scattering matrix. Essentially, the scattering matrix that I showed to you on the previous slides is just the inverse of this matrix. So let's see if we can learn something more about this matrix now that we have a chain of n bosons. But since this is now a much bigger matrix, this is not so simple in general. But here we can use something we know from condensed matter physics and go to periodic boundary conditions. So this means that we just close the chain to form a ring. And in that case, we know that we can easily diagonalize this matrix, so calculate the eigenvalues, by going in a plane wave basis, or by introducing a quasi-momentum k. Now, if this were a condensed matter Hamiltonian, we would get energy bands from this. So this would be the eigenvalues, and we get this energy dispersion relation. But crucially, this is not a Hamiltonian, and indeed, this is not even a Hermitian matrix. In general, this need not be a Hermitian. As we can see, this prefactor here is in general not the conjugate of this, which we would require for this to be Hermitian. In general, it's non-Hermitian, and this means complex eigenvalues. So, and what this brings us to is the curves that I showed to you in the beginning. So the eigenvalues of this matrix typically wind in the complex plane, and they can enclose the origin or not. And this enables us to define a winding number. Now, I've written down the definition here, but essentially what it just does is count how many times this function winds around the origin. But now we want to go back to open boundary conditions, go back to the chain that we are interested in. And by opening the boundary conditions, what we'll see is that whenever the winding number under periodic boundary conditions is not 0, then this corresponds to directional amplification in the system under open boundary conditions. There's also quite an intuitive way to understand this. Let's go back to periodic boundary conditions. So what does it mean to have a non-trivial winding number? Well, this always implies that there are some eigenvalues which have a positive real part, as you can see, if the winding number is to be non-zero. But this also means that with the definition of our dynamic matrix, that there are unstable solutions. So it's also quite easy to see that non-trivial topology requires some kind of non-reciprocity in the system. So what happens under periodic boundary conditions is that excitations hop directionally around this ring, And because we have unstable solutions, we also get growing solutions in time. So there's gain over time. But now we go to open boundary conditions and we remove one link, and this interrupts this motion and leads to essentially just to a pileup of the excitations at one end, and then they can be extracted from the system as directional amplification. And good news is this also makes the system stable, so we can actually use this to build a device. To make things a little bit more formal, we also derived a quite useful decomposition of the scattering matrix in our paper that shows this quite clearly. And this decomposition consists of the square root of an amplification gain and some functions that shape the scattering matrix. And so if we look at this example for nu equals -1, this leads to one very dominant matrix corner element, and the others are all suppressed. And in particular, this means that if we have a signal incident on the first cavity in the chain, in this particular example, there's directional end-to-end amplification to the other end of the system where this exits again. The opposite is true for nu equals +1, where this is just amplified to the other end. We also have an analytic expression for the gain, and we can show that indeed the gain grows exponentially with the number of sites that we have in the system. So if we scale up the system, make the chain longer, the gain gets much bigger. And at the same time, the reverse gain is exponentially suppressed with the number of modes. And then there's one special point in the system that is particularly useful if you think about realizing such a device, which is the exceptional point, at which the reverse gain is always exactly 0. Now, from this decomposition, we can also recover this case that I started with by setting n equals to 2, and then we get exactly the scattering matrix that I showed you in the beginning with just the square root of the amplification gain on the off diagonal. So when we now think about the topology of the role of topology, what we get is a topological phase diagram, which at the same time is a phase diagram for the scattering matrix. So I show here the phase diagram. On the x-axis, I have a quantity that is proportional to this dissipative coupling strength that I showed to you before. And on the y-axis, there is this phase theta, which essentially controls non-reciprocity in the system. And we get 3 different topological regimes. These orange lobes are the regimes where the winding number is non-zero, whereas all the rest is trivial. And so when it's non-trivial, we get these matrices that I just showed you before with this one dominant corner element, which means that there's directional amplification. Whereas whenever we're in a trivial regime, well, we can still have non-reciprocity, but there's no meaningful gain. So it's always of order 1. And even more crucially, when we make the chain longer, the gain is attenuated with system side rather than growing. And then I also show when the system is dynamically stable. So all the gray region is when the system is dynamically unstable. So if you actually wanted to build a device, it would be good to stay here in this regime where it's dynamically stable. So far, I've only shown you what happens with an ideal translational invariant system, but I'd like to quickly show you something that is a bit more that is what we're working on at the moment. Namely, what happens when we have disorder in the system, which is quite realistic. We can't assume that all the cavity frequencies are the same and all the decay rates. So let's have a look at what happens when the decay rates or the frequencies are disordered. In general, of course, the other quantities can be disordered, parameters can be disordered as well. And actually, we can show that then, at least qualitatively, what I'm going to show you next applies as well. So let's just stick to on-site disorder for now. And we also assume that the disorder is bounded, so it means that the absolute value of the disorder does not exceed some disorder strength W. So the first thing we looked at was the spectrum. Let's do the same thing now again. Without disorder, we got a curve that winds around the origin, and that was this green dashed line. Now with disorder, what happens is that this curve smears out and we get an area that contains all the eigenvalues of any possible realization. So if you have a system with disorder, you calculate the eigenvalues, then they're going to be in this green area here. And what it turns out that if you're now interested in directional amplification, all you need to do is look at the inner and outer bound of this area, and that when these are still topologically non-trivial, you can be sure that there will be directional amplification in the system. So in particular, what you need to make sure in this case is that the minimal separation between the spectrum without disorder, so this green line, and the origin is larger than the disorder strength, because this sets the width of this area. And we call this separation point gap in analogy to condensed matter systems, because there's a quite similar argument, as you'll see in a second. But what happens if the inner boundary is not topologically non-trivial anymore? Well, in that case, we just can't be sure. So there's some probability that the system is still non-trivial and we get directional end-to-end gain, so that's great. But there's also some probability that the transport will look trivial. So in other words, we get a decay and no meaningful gain at the other end. And as I said, this is quite analogous to what we know from Hermitian systems, where when we have a band gap and a mid-gap state, then the amount of disorder that is tolerated is essentially just set by the energy gap. And just let me finish with this. We can also use these bounds to provide bounds for the gain that we get in the system. Before I showed you that without disorder, the gain grows exponentially with the number of cavities that we have in the system. So that's the original gain. We have an exponential growth. And very nicely, this is still the case when we have disorder in the system, but maybe the exponent is slightly different, but it's still an exponential growth with system size that bounds the gain. So it really pays off to scale up the system because you gain a lot more. And finally, just a quick outlook. We also looked at the reverse gain and found that this is extremely robust as well. And the exceptional point that I highlighted to you before, where we had this reverse gain that was exactly zero, also is robust. And in fact, if we only have on-site disorder, it doesn't matter how strong the disorder, what type of disorder, the reverse gain is always zero. So it's quite a surprising result. But so this shows us that the exceptional point is really the optimal working point for a directional amplifier. Okay, and with that, let me finish and thank you for your attention. And if you're interested in more details, then I'd like to point out these references to you. But I'm also happy to talk with you, chat with you further. So if you have any questions, just send me an email. Thank you.
Oh, fantastic talk, Clara. Really nice talk. So any questions for her? If there is no question, then we can move to the third talk.
I have a quick question, Saba, if that's okay.
Yeah. Sure.
So super quick. So this might be a really naive question. First, really clear talk. Thank you so much. To generate these like cavities in a ring, could you do it, for example, by like micro-engineering them on a chip or something like that?
Actually, so there have been realizations with, for example, microwave circuits, and these can be done on chip. So there are, if you can, there's, for example, from Mika Zilampa and the group of Mika Zilampa, they have actually built this with cavities. I mean, it's not exactly the same system. It's just essentially one unit of the chain that I showed, and it's a slightly different model, but you can do this. So this is actually not, and there are other examples. It's just the first that came to mind. So you can. This is not something that I'm just doing, that theorists dream about, but this can actually be done. So yeah.
Oh, that's really exciting. Thank you.
You're welcome.
Any more questions? Okay. If not, then we can move to our third talk. We are very short in time. So the third talk will be given by John. He's a final year PhD student in the Quantum Measurement Lab at Imperial College of London. And he's been supervised by Dr. Michael Vanner and Dr. Joshua Nunn. And today he will be talking about single and multi-phonon subtraction in whispering gallery mode micro-resonators. So John, now the floor is yours.
Can you hear me?
Yeah.
Cool.
Yeah.
Cool. So first, just thank the organisers for asking me to do this talk. And without further ado, I'll get into talking about some recent experiments in our lab, which is on single and multi-phonon subtraction to thermal states in whispering gallery modes using Brillouin optomechanics. Just a quick summary of what I'll be talking about. I'll quickly outline the motivation for this talk, talk a bit about Brillouin-based cavity optomechanics for those who are not familiar. I'll then talk about some work on single phonon addition and subtraction. Then I'll discuss how this doubles the mean thermal occupation of that state. And finally, talk about how this can give rise to non-Gaussian mechanical motion and touch a bit on some outlook stuff. So motivation. So why would you want to do these kind of single quantum level addition and subtraction operations? So I guess there's kind of three main reasons. You might want to do this to engineer some quantum states of motion, which is kind of pertinent to the title of this talk series today. But you may also want to use these operations for quantum information and communication operations, for example, distributing entanglement across a quantum network. You can also do stuff like programming some fundamental physics that is kind of like the order in which you do addition and subtraction operations. Do they obey bosonic commutation relations, for example? And there's been some work in optics already done on that. So Brillouin optomechanics using whispering gallery mode resonators. So Brillouin scattering is a chi-3 nonlinear effect, and it couples two photons to one acoustic phonon. And at 1550 nanometers, you gain access to gigahertz frequency phonons. This interaction comes about because of a combination of electrorestriction, where the optical intensity modulates acoustic vibrations in the medium of choice. So we can think of the optical forces compressing and stretching out the localized structure of the medium, and also photoelasticity, where these density modulations in turn modulate the refractive index of the medium. And in the work we're going to be talking about today, we'll be talking about thermal scattering, which is also sometimes known as spontaneous Brillouin scattering in the literature. And here, a thermally excited acoustic wave in the medium acts as a sort of Bragg mirror, which can kind of up or down shift the light depending on your configuration. So in Stokes scattering, an incident field scatters off a co-propagating acoustic wave, and you get a downshifted photon. And conversely, in anti-Stokes scattering, your incident optical field interacts with a counter-propagating acoustic wave, and you get a up-converted light field. Okay, so crystalline whispering gallery mode micro-resonators, which is the platform of choice for our experiments. So there's a photograph here from our experiment where you can see a crystal with some whispering gallery mode bulges, as we call them, machined into it, and we couple light into the structure with a tapered optical fiber. And light circulates around the circumference of this structure with something like the inset there, which is kind of the transverse mode structure of that optical mode. And we like this platform for a number of reasons. The first three are kind of, you get high mechanical frequencies, as I just touched on. You get low mechanical damping at cryogenic temperatures, and some of the best mechanical QF products have been demonstrated in such systems. You also get low optical absorption because this Brillouin scattering interaction can take place in any optically transparent material. And these three properties are advantageous because they give you a certain robustness to thermal decoherence. And the second set of properties is you get low intrinsic and radiative losses in the whispering gallery modes. you get small mode volumes, and you can get significant intracavity buildup, all of which help you on the way to achieving strong optomechanical coupling. And how we use these resonators to perform Brillouin optomechanics is as follows. So we typically find two cavity modes that are separated in frequency by the mechanical frequency. And typically these are two different transverse, two modes with different transverse optical structures. And I should point out that there's never usually a third mode on the other side. It's two and only two modes that are separated by the frequency. And if we pump with a strong coherent tone on the higher frequency mode, we can do Stokes scattering. And in the linearized regime, it gives rise to a light mechanics two-mode squeezing type of Hamiltonian between a mechanical mode B and an optical mode A with some coupling strength G. So in our kind of whispering gallery picture here, we have our pump tone going around and scattering with a co-propagating wave. Similarly, if we want to drive anti-Stokes scattering, we switch the pump mode and we pump on the lower frequency mode. It scatters into the higher frequency mode by interacting with a counter-propagating acoustic wave. And here we give rise to a light mechanics beam splitter type Hamiltonian. And I give some kind of rough order of magnitude. I quantify some of the key system parameters to a rough order of magnitude in this table. So the mechanical frequencies are typically of gigahertz. At room temperature, the mechanical decay rates are typically a megahertz. Optical modes can be anything like 1 megahertz to 100 megahertz. The vacuum optomechanical coupling rates are roughly 100 hertz, and through the pump enhancement, we can get G's exceeding kind of megahertz level. So we're operating well within the resolved sideband regime. And what is nice also about the system is it's a triply resonant system. So we have our two optical fields resonant with cavity modes, and we also have to obey strict phase matching conditions for the Brillouin interaction. Okay, so now I'll talk a bit about the actual single phonon addition and subtraction work. So to set the scene, it's probably useful to first talk about single photon addition and subtraction. So you can imagine to perform single photon subtraction, you have a thermal state impinging on a beam splitter with optical vacuum on the other. And if we get a click on one port, it means that we've subtracted a photon from that impinging thermal state. And similarly, we can imagine that we're weakly driving a two-mode squeeze interaction in something like spontaneous parametric down conversion. And if we get a click in one mode, then we've added a photon to the output mode. And curiously, what these operations do is for the case of single photon addition, we increase the mean occupation from its original occupation n bar, obeying this black line, to 2n bar plus 1, obeying this red line. And similarly for the single photon subtraction, we double it, but we don't have the +1 factor because you can't subtract from the ground state, but you can always add to it. And these two are equivalent in the high n-bar limit, as is kind of evident from these equations. And I should say that I've been talking about this photon stuff, but because the mechanics and the optics are both bosonic systems, the two are kind of equivalent, and it helps to set the scene. So it might be a bit counterintuitive as to why exactly the occupation effectively doubles when you do these operations. And we can kind of gain an understanding of this if we think about the Bayesian inference using the measurement outcome. And as a simple but crude example, imagine that we can somehow prepare a superposition of state as our input state. Imagine we can prepare our input state as a coherent superposition of 0 photons and 100 photons. Then our mean occupation before the interaction is 50. We then get a click, and if we get a click, it must mean that we were initially in the 100 state. Therefore, we must now be in, there must now be 99 photons. So therefore, we've effectively doubled the mean occupation from the information we gain from that. So I'll now move on to talking about single phonon addition and subtraction, which is a little bit more complicated than the picture that I just outlined, because there's no way to measure the mechanics directly. So instead, we have an optomechanical interaction where information about the mechanics is mapped onto the optical cavity mode, which then leaks out of the cavity, and we can detect on that optical mode. So when we get a click on the output of the optomechanical beam split or two-mode squeezing interaction, then it gives us information that an addition or subtraction operation must have happened. And then we can perform heterodyne detection on the same field to verify that the operation happened. And we're doing this to kind of see that the mean thermal occupation has indeed approximately doubled. So in an experiment, I'll just talk about the addition case. So in an experiment, what we would do is we would pump on the higher frequency mode, and we get a signal scattered at the lower frequency mode, and we detect a photon on there, and we also perform heterodyne detection. And this is the experimental setup that we used to do this. So we send a strong pump light into our optical cavity, and the light the signal tone back scatters out. We then pick off this backscattered signal, and after some filtering, we detect a photon on it. And that gives us a trigger signal to then take a time trace of our heterodyne detection on the same mode. And what we get out for a single time trace of the heterodyne detector is something like the left-hand side for optical vacuum, and something like the right-hand side for when we have an actual optomechanical signal impinging on the heterodyne detector. And we can see that for a single trace, there's a bit of a difference, but nothing too meaningful. So what we have to do is we have to repeat this measurement thousands of times to build up sufficient statistics to average through the noise. And when we do that, we get something which looks like the traces on the left-hand side. So the top is for addition and the bottom is for subtraction. And the gray lines indicate optical vacuum. And there's three kind of pertinent features. We see far away from a click event, which we signify with T0 here on the x-axis, that there's a sort of baseline heterodyne. Oh, sorry, I should have said earlier that what we're plotting here is the variance of the heterodyne signal. So we see that far away from a click event, we have some baseline variance due to the optomechanical signal, which I've kind of highlighted with B. And then at the time of a click, this increases to value A. And when we do this 20,000 times, as shown here, we see that the variance approximately doubles in both cases, and the variance is a proxy for the occupation of the mechanical state. And this is in good agreement with the theory work. So we were pretty pleased with that, but then we moved on. So these operations actually give you some non-Gaussian mechanical motion, and I'll now go on to talk about that. So the scheme to observe this is very similar. So we generalize what we did previously, and we instead kind of expand to be able to detect n photons on the output mode of the cavity. And then when we do that, we perform state readout and tomography on the conditioned state to reconstruct the phase-based distribution. And in this work, we only considered the case of subtraction, because it's much more well suited to state readout because of the light mechanics beam splitter interaction, where the light is a proxy for the mechanics. And in the case of the two-mode squeezing, the interaction can lead to instabilities such as lasings. So we want to kind of avoid that if possible. So how do we do the state readout? So we're kind of lucky that the states we generate using this scheme are phase invariant, and that is because the initial states are thermal and therefore phase invariant, and the optomechanical beam splitter interaction and subtraction operations both preserve this, as they are also phase independent. So we can generalize the quadrature that we measure to be this rotated quadrature, and we can then mix down what we measure at the heterodyne frequency to extract the X and P components in a technique that's called IQ demodulation, and that's quite a standard technique to do this. So the experimental setup to do this was very similar. The only addition is that we've added a beam splitter on our detection port, so we can detect either 1 or 2 photons. So either look for single clicks or coincidences and trigger the scope on that and record heterodyne time traces. So when we do that for many tens of thousands of times, and we perform IQ demodulation on the time traces, we can build up a phase space distribution which looks as such. So we have in the left-hand panel, we have the initial mechanical state where we don't condition on clicks, so 0 subtractions, and we have in the inset there the optical vacuum for reference in size. We find that when we perform a single click, so we subtract 1 phonon from the mechanical state, we generate a kind of ring-like structure in mechanical phase space, and we see this non-Gaussianity appear. And then when we do 2 phonon subtraction, we see that this non-Gaussianity grows, and the effect of this is much more prominent. So the white dashed dotted lines indicate theoretical predictions for where the maxima of the phase space kind of peaks should be, and we see good agreement there. I should note that these quadratures are normalized to the mechanical 0-point motion, which we were able to do through a few measurements in the setup. And I should talk a bit more about the phase spaces I'm showing you here. So these are S-parameterized Wigner functions. And the reason that they are this is as follows. Because we're performing heterodyne detection, we're measuring the X and P quadratures simultaneously. So that convolves the Wigner function with optical vacuum noise, and in fact, we would reconstruct the Husimi Q function.
John, 2 more minutes, please.
Oh, thanks. Because of inefficiency and loss, we then introduce even more optical vacuum noise, which is captured well by this S-parameterized Wigner function. And our measurement was very inefficient and lossy. Therefore, this was the most suitable measure to quantify that. So once we have the phase space distributions, we can kind of then get any measurement statistics or probability distributions that we would want to get. So from this, we then calculated the quadrature variance, similar to the first set of results that I was talking about. This time normalized to the mechanical vacuum point and indicated by sigma rather than X. And we see that for the single click case, the mean occupation effectively doubles again, and for 2 phonon subtraction, it effectively triples, which again, the dots here are experimental data and the solid lines are theory curves. We might also want to look at the quadrature distributions. So these are the marginals at the time of the click. And we see that the initial state shown in blue becomes non-Gaussian for 1 click, 1 subtraction, and this non-Gaussianity grows again further for the 2 click, 2 subtraction case. And we can also record these for the various time points, and we see the time evolution and the kind of non-Gaussianity being created and dissipating away. So to summarize, I've outlined some of the motivations very briefly for these single phonon addition subtraction operations. I've talked briefly about how we implement them and the scheme we use to do so. And I've outlined Brillouin optomechanics using whisper and gallery mode micro-resonators and why we think it's a good platform to do these operations in. We've observed the approximate doubling and tripling of the mean thermal occupation when performing these operations, and we've also seen non-Gaussianity in the phase space and marginal distributions of the prepared mechanical state. Moving forwards, one might want to perform these experiments at cryogenic temperatures where you get improved mechanical cooperativity, which in turn would allow you to achieve a higher overall measurement efficiency, which allow for better phase space tomography. And then further down the line, one might want to perform more advanced state preparation protocols to create non-classical states of mechanical motion. And I'd like to thank you for your attention. You can find these works at the displayed references, and here is photographs of everyone involved in this work and all the associated institutions, etc. Thanks for your attention.
Thanks very much, John, for the nice talk. Do we have any question from John? Oh, Marcus, can you unmute yourself? Yeah.
Yes, thank you very much, John, for this nice talk. I have a question regarding the resonators in the actual experiment. You said you machine them. Do you actually do this in-house, and how do you get these bulges on them, and what's the challenges with getting these bulges?
Yes, so we don't machine them in-house. So our collaborators in Canberra in Australia make them. So Jerry and Baveen were the two guys who make them. And they make them by starting with a bulk sample of crystal and then machining it down with a diamond nanolathe. And we've only had 2 resonators made from them so far, so it's still quite a new process. So I couldn't really speak on the challenges, but I think the biggest one is the delicacy of the crystals. Yeah.
Thanks.
Do you have any variation in frequency and quality factor in these resonators?
What do you mean by as in from sample to sample?
If you have 2 resonators, then each resonator does have the same frequency, or how consistent they are? Yeah,
so the mechanical frequency in Brillouin scattering is essentially set by the speed of sound in a material. So that is kind of a baseline value, but then we get some geometric dispersion effects. So for the particular kind of acoustic whisper and gallery modes, you get a small variation, but broadly speaking, they're roughly 8 gigahertz for these barium fluoride resonators that we've been using. And the quality factor is dependent on how the fabrication process went. Mm-hmm. And also just the kind of degradation over time as the resonator gets a bit older.
Uh-huh. Yeah. Thanks. So we do have a question from YouTube chat from Patrick. He said, "Hi, John, very nice talk and nice results. Are you considering higher than n equal to 2 subtraction? Is it just more detectors needed or photon number resolving detection?"
Yeah, exactly. So we only did up to 2 phonon subtraction in this work for technical reasons. So we were using APDs. So the measurements to get the required statistics for the 3 subtraction case would just take a long time. And the theory work that we've kind of got to go alongside this work just predicts that the ring gets a bit bigger, and there wasn't too much benefit in doing it for more than 2 subtractions, really. Yeah.
Yeah, cool. Any other question? Yeah, so Sophia, can you ask yourself?
Yes, of course. So thanks everyone for really nice talks. So I had a question for Ricardo after his talk, and I was wondering what the main application of these really nice cat states that this protocol can create. What the main applications of them would be.
Hi, Sophia. Thank you for the question. So so one one application would be quantum metrology, for instance. So basically, these states, these non-classical states, are very sensitive to the parameters of the harmonic oscillator. So basically, of the Hamiltonian. So you could boost the basically the sensitivity of your estimation. But as you said as well, basically for testing fundamental physics, like I don't know, gravitational effects in the superposition of two of your system, could be also interesting. So, but we didn't think about it.
Okay, thank you.
Okay. So now we have come to the end of this session. Mudassar, would you like to?
Yes, actually, I had a few questions, so I'll take this opportunity to take over and ask all the questions I wanted to ask. So it's a really quick question. I was just curious with John, how do you work out the non-Gaussianity? I mean, it's obviously sometimes it might be clear from the distribution, but is there an additional methodology that you're using in determining more concretely how non-Gaussian your state is?
Yeah, so that's a good question. And I think in our experiment, we're very limited by our overall measurement efficiency. So our overall measurement efficiency was roughly 1%. So that's including the kind of transduction from light to mechanics in the optomechanical interaction, and then cavity losses, and then by the time it makes its way to the detector, and then the heterodyne detection also. So I think to get in a regime where you're kind of more, for want of a better word, deterministically kind of looking at it, you would need to be in a much more efficient regime, such that you could start to not need so much statistics to get through the noise.
And the other thing, I may have missed this point, but you didn't go above n is equal to 2.
We
what
did.
Was the reason for that?
Sorry, so we is your question how many subtractions we investigated? Yeah. We did.
Like, as in, what was the limit to that?
Yeah, so we did double subtraction. So that's looking at coincidences on the heralding arm. And we didn't go above that because at the start, we didn't have access to more than 2 detectors. But then when we did get access to it, we would have to measure for basically a week to get the statistics on 3-fold coincidences. And because all we're seeing then is the ring in the non-Gaussianity grow again, we didn't think it gave too much extra benefit versus the measurement time.
Thanks. If it's okay, I know we're well past the time, but I had a really quick question for Ricardo as well. I was just curious. If Ricardo, if in your sort of almost state preparation or engineering with this with adiabaticity, if you considered what would happen with introduction of different types of decoherence mechanisms, or even when it's coupled to different types of baths specifically. So here I was more interested in like colored baths, for example, or baths that have a very specific engineered spectral density.
So in our case, we didn't consider a noise or decoherence, and this is precisely because, in principle, with these protocols, you can speed up the evolution as much as you want, basically. But of course, there is always a limitation of what you can achieve experimentally, right? I mean, this will set how fast you can do it. But in principle, this was the main motivation to remove the coherence from the picture in a way. But of course, if you include that, then this will spoil the efficiency, right? I mean, a bit depending on how fast you do it or not. But we didn't look into that into many detail.
Okay. No, that's good to know. All right, thank you so much. So once again, thank you all to our 3 speakers and Saba for chairing. Been really enlightening and educational for me. It's really nice to hear you all talk. So thank you once again, and thank you everyone for joining us. Apologies, it's taken a bit longer to wrap up today. Till next week, as a reminder, is a break, and then please join us again for a really exciting discussion beyond the quantum ground state, And we'll have 4 panelists chaired by Michael Vanner. I'm very excited to hear that discussion, and I'm sure everyone here would be as well. So please also share widely. We have backgrounds from various different communities, from ion trapping to from electromechanical systems to, of course, optomechanical systems. And the idea is to discuss in depth this idea of what to do beyond the quantum ground state. So please join us then. But until then, please have a great week, and then see you in 2 weeks. Bye.